Following public requests, today we're going to speak about logics. But I'm going to speak about logics in a very non-conventional manner. For example, I have planned to tell you we're going to do intuitionistic propositional logic with whatever set of rules you imagine, and I won't write any. So perhaps I write a few ones. But, it's not that important. The point is the construction we are going to make and the relation to stone duality. So we will start with a logic. I haven't exactly decided which one, but typically I would like to do something like propositional classical logic, intuitionistic classical logic, and some modal logic, probably S4 because it's one of those I love most. So anyway, let's start with a logic which is propositional. It has formulae F, G, etc., which is a fun thing I usually say to my students, that the etc. has a kind of limited length, because after some time letters collide into other letters. And the worst case is when I say variables are going to be written X, Y, Z, etc. So anyway, for formulae, I'm going to take atomic formulae, or propositional variables, and a few other kinds, like conjunction, and, disjunction, or. I'm not sure I like negation, so I'll take false, implication, and F implies false is negation. Anyway, a standard problem in logic, well, which has been well solved for something like 1 century, is completeness of an axiom system. So, on the one hand, you have a semantics. For example, for classical logic, you can say when one of those formulae is true. Or you first have to say which atomic formulae are true, and then you say F and G is true if and only if both F and G are true, and so on. And you have a deduction system, whatever it is, reasonable one. Okay? So logicians may think about natural deduction, sequent calculi, and so on. I will actually use something like Hilbert systems, although you can't do any proof search in any reasonable Hilbert system. So any reasonable proof search. This will be more practical here. So essentially, a Hilbert system is a list of axioms, something like, well, I want F implies G imply F imply, so I want F to imply G implies F. A few axioms like this, plus rules like one which says that if you can prove F implies G and if you can prove F, then you can deduce G. And the point is, now imagine that, so it's easy to prove that if you can prove something in that system, then it's valid. So it's true whatever the truth status of atomic formulae. That is soundness, that is an easy induction on formulae. If you don't manage to prove it, perhaps you haven't got the right proof system or you've got the wrong semantics. But you must be able to prove it if it's true. My problem is completeness. Completeness is the converse property. So the converse property is, imagine I give you a formula that is valid. That is, whatever you do, it's always true. And I want to deduce that you can prove it with a finite proof. And that sounds harder. Okay, it is harder. Using contraposition, you see that the problem is, imagine I can't prove F. Can I build a model that is for classical logic, it's very simple. It's just, can I build an assignment from the propositional formulae, atomic formulae, sorry, to true and false that makes the formula false. And I have to find it. Okay, instead of giving you a complete construction, I'll tell you that a fantastic thing in mathematics and probably in the whole of science is that it's structured in communities. Different communities, you realize that different communities actually discover the same theorems with different vocabularies, and eventually, in some cases, they actually have invented exactly the same notions. And in that case, the two communities are logic and topology. They are not disjoint, by the way. Recently, I was rereading a paper by Robert Goldblatt, who's an Australian logician, and it's a paper that's called Topological Proofs of the Rashowa-Sikorski lemma. The Rashowa-Sikorski lemma is a lemma that's used to prove completeness of more complicated logics than just propositional logics. That is, first-order logics, typically, including first-order intuitionistic logics. But Robert Goldblatt is a logician, and he's written a paper on topological proofs. And essentially, that's because that lemma, which is a lemma from logic, or from order theory, if you prefer, can be proved by the use of the Baire category theorem in topology. But I won't talk about that today. So, in logic, the way you try to prove that thing complete, there's a method called Hinticke sets. So Hinticke sets are really for first-order logic. They're kind of degenerate for propositional logic. But typically you take a set gamma, they like to use big Greek letters. And that set gamma should obey a certain number of conditions. And typically, conditions like if f and g is in gamma, then f is in gamma and g is also in gamma. If f or g is in gamma, then f is in gamma or g is in gamma. You can't have f in gamma and not f in gamma. So it's not the case that f is in gamma and not f is in gamma. So let me remind you that not f is f implies false. And you do a few things with that kind of set. So first you show that such sets exist. In fact, those are the sets that are built during a Tableau proof search procedure. And but here's another view on Hinticke sets. And this is a view that's sometimes found in other completeness proofs, so based on something called maximally consistent sets. And in that case, you use sets gamma, which are consistent. So that is, you can't deduce false from gamma. And I should add that in the previous case, that is not equivalent, but it's in the same spirit as saying that false is not in gamma. But we have not required that a Hinticke set is closed under deduction. An Hinticke set doesn't need to contain every consequence of any formula you've put in an Hinticke set. For a maximally consistent set, it's not in the definition, but maximally consistent sets are closed under deduction. That is, if f is in a maximally consistent set and f implies g, then g is also in it. But the usual definition is not this one. So you take a consistent set, so it's a set where you can't deduce false, and it's a maximal set. That is, you can't add any formula to that set without making it inconsistent. And a basic lemma of that theory is that all those maximally consistent sets are closed under deduction, as I said, meaning that if f is in gamma, and you can prove that f implies g, okay, so I have implication, but really I want to consider implication as an ordering. So writing this is not what I want to say, because this is actually a piece of syntax here. It's just a piece of text. It's inert. It doesn't say anything. So I should say if this is provable. But that actually defines a pre-ordering. So let me write it this way. Right? So f implies g means you can deduce g from the assumption f. And the deduction theorem tells you that it's equivalent to saying that F implies G is provable from no assumption. So if F is in gamma and F is less than or equal to G, then G is also in gamma. You can show that a maximal consistent set is actually the Intica set. So, but it has more properties. For example, it has the reverse of that property as well. It has the property that if F is in gamma and G is in gamma, then their conjunction is also in gamma. The proof is always the same. So you assume that F and G are in gamma, but F and G is not. So you add F and G, you know what you will get is an inconsistent set because the previous set was maximally consistent. So anything you add, which was not there before, must cause an inconsistency. And then from that, you deduce that the inconsistency must have been present in gamma already because from F and G, you can deduce F, you can deduce G. And so anything you can, if you can deduce false from anything using F and gamma, using the formula F and gamma, you can also deduce it by using both F and gamma separately. And they were already in gamma. So if gamma union F and G was inconsistent, then gamma containing F and containing G was already inconsistent. You can realize that if F or G is in gamma, well, certainly F must be in gamma or G must be in gamma, and it's again the same argument using maximality, in fact using ultraposition as well. So if F is not in gamma and G is not in gamma, you want to prove that F or G is not in gamma, and excuse me?
So this is an axiom of Intica sets.
Yeah, this is an axiom of Intica sets, but now I'm describing maximally consistent sets. So I should say that in a Intica set, so in a maximally consistent set, since it's closed under deduction, in particular it satisfies this. And we also have the converse. And we also have this axiom of Intica sets. And so imagine that F is not in gamma, G is not in gamma. So that would mean that if you added F to gamma, you would get an inconsistency. So from F plus some axioms of gamma, you would get false. From G and some axioms of gamma, you would get false. And usually there's a rule in logic which says that if F or G and a set of formulae, then either F or G, and if you can deduce the same thing, in that case false in both cases, then you can deduce false from F or G. But if F or G was in gamma, you couldn't deduce false from gamma because gamma is consistent. So you have all these conditions. So what I'm saying in particular here is that that technique of proving completeness using maximally consistent sets, so I'm not saying how you prove completeness, I should probably say word. So typically using maximally consistent sets, what you show is that, so I let out a big word. So typically assume you can't prove F. Okay? That means that not F is consistent. And then you use Zorn's lemma. So not F is a one-element set. It contains, sorry, I should say, open curly brace, not F, closing curly brace, not F, okay, is a one-element consistent set. And using Zorn's lemma, you can show that every consistent set is included in some maximally consistent set. The only thing you have to show is that the set of all consistent sets ordered by inclusion is an inductive Poe set, or equivalently for domain theorists, a DCPO. It's not equivalent, but every inductive Poe set in the literature I know of is actually DCPO. And so you only have to show essentially that if you take any chain of consistent sets, its union is again a consistent set. Inconsistent means you can't prove false. but the proof is finite, so there's only finitely many formulae. So you can only use finitely many formulae from finitely many elements of the chain, and that is why it's inductive. The rest of the argument is an exercise. So anyway, so if F is not provable, not F is consistent, hence it's in some maximally consistent set, and what do you do next? Well, that maximally consistent set has a funny property, which is that, I forgot to say that, but we have this property that you can't have both F and not F in the maximally consistent set, but in fact, if you take any formula F, either F or not F must be in it. By essentially the same argument as here. Okay? So you have that for every formula, F is in gamma, exactly one of F in gamma, not F in gamma, holds. And so in particular, if you look at atomic formulae, in your maximally consistent set, either you've got A or you've got not A, but not both. Okay? And that gives you an assignment of truth values to the atomic formulae. Decide that A is true if and only if it appears in the maximally consistent set and false otherwise. And with that, you can prove by induction on formulae that a formula is true under that assignment if and only if it belongs to gamma. Hence, since not F is in that maximally consistent set, not F is true under that assignment. So F is false. So that's a kind of quick completeness argument. My point is first to tell you what the connection between these two things is. So maximally consistent sets are integer sets. But conversely, if you take the upward closure of a integer set, well, yeah, up to, no, it's not the upward closure, but every integer set is included in a maximally consistent set. And in logic, integer sets are pretty nice because you don't need them to be closed under deduction, and that makes it easy to work with, especially in first order logic, where you have to introduce another nasty condition on existential quantification, which is hard to deal, so I'll skip over that today. As a hint, this is why the Rashova-Sikorsky lemma is useful. The Rashova-Sikorsky lemma was invented to deal with existentials using that kind of technology, and probably because integer sets were simpler, the Rashova-Sikorsky lemma was essentially completely forgotten, and people use integer sets instead. So anyway, what I wanted to say is that we're going now to work towards topology. So you have a preordered set of formulae. The preordering is implication. And what I have said here is that a maximally consistent set is something that, I never said that it should be non-empty, but one of the consequences, I haven't put a true in it, but you can code true as not false. Okay? And not false must be in it. Not false must be in any maximally consistent set, because you can deduce not false. So it's, okay, it's again the same exercise. It's maximal. If it were not in it, you could add it, it would cause an inconsistency, and you would get a contradiction this way. So it's a non-empty set, always. It's upwards closed because of that property. Okay? It's closed under conjunctions. Any reasonable proof system will say that F and G is a infimum of F, comma G. Okay? So F and G implies F, so is below F, implies G is below G, and so it's a lower bound, and it's a largest lower bound, it's not the largest lower bound, because we are in a preordered set, and anything that implies both F and G must imply F and G. That means that anything below F and G is below, so anything below both F, comma, and G is below f and g. So that means that f and g is a greatest lower bound or an infimum. So here this condition actually says we have a non-empty upwards closed set which is closed under binary infima. Does it remind you of something? Who will have the courage to, who will dare say the word?
Filter.
It's a filter. Okay, what does this property say? Ah, okay. An ultrafilter is this property. This says it's a prime filter. Yes. But ultrafilter is a stronger property than prime filter. If you're doing classical logic, the set of formulae is going to be, let me call that a pre-Boolean algebra. So it's a Boolean algebra, except that some formulae may be equivalent but not equal. So if you want to be pedantic, that means that if you take the so-called Lindenbaum algebra, which is a quotient of the set of formulae by the equivalence relation of being mutually less than or equal to each other, okay? So that's called the Lindenbaum algebra. It doesn't do much, actually. What you get is a Boolean algebra, okay? So if you start from classical logic, if you start from intuitionistic logic, what you get is a so-called Heiting algebra. And I'll say, oh, we have said something about complete Heiting algebras earlier, a few months ago, and that was a frame, right? That was the same thing as a frame. So I'll say a bit more about Heiting algebras later for intuitionistic logic. So anyway, without any proof, indeed here, that technique of maximally consistent sets for classical logic produces ultrafilters. Okay. If you start from intuitionistic logic, in fact you won't have this property, but you will have this one, and what you will get is prime filters. The funny thing is that if you start from a pre-Boolean algebra, any prime filter is actually an ultrafilter. The two notions are the same in a Boolean context. In a Heiting algebra, every ultrafilter is prime, but the converse is wrong. And the right notion is the notion of prime filter. So anyway, let me tell you about prime filters. Well, I've lied to you all along. So I tell that to my students regularly, that I'm a liar. So I tell them, okay, I'm regularly lying. And then sometimes I tell them, oh, I lied. That proof is wrong. Where's the mistake? Or sometimes I tell them, oh no, that was a simple explanation. That was so that you understood the spirit. But there's a difficulty. Remember, I said this, but this is actually not true in general. So what can you assume to make that true? So we add an assumption, blah, blah, blah. So I lied to you for something like 6 or 7 sessions. I told you about stone duality. Probably told you, actually, I tried to fix that lie somehow by saying this is not the original stone duality. What I have told you about is a modern form of stone duality. But the original form that Stone invented in 1938, in 2 papers, by the way. The first one is the original stone duality for Boolean algebras, and the second one is for stone duality for distributive lattices. So what does Stone do? Well, let's start from the first paper. He takes a Boolean algebra. Funny, essentially is our situation. Okay? And then he builds a space, topological space, whose points are all the ultrafilters. I wrote prime filters here, but as I've just said, without any proof, prime filters in a Boolean algebra are ultrafilters. That's the same thing. So he builds a space of ultrafilters with some topology, and that topology is built in a very, very familiar way. So typically, if you take an ultrafilter U, it's going to belong to the open set. So the open set will be indexed by elements of the Boolean algebra, or by formulae if you prefer here. So since that is a notation that I've seen recently, I use it. Okay? And you define the open set, defined by the formula F, as being the set of ultrafilters that contain it. So that U, an ultrafilter, or a point of the space, is in the open set associated with F, if and only if formula F is in the ultrafilter U. And it's a familiar thing because, as you remember, we have done that already, to say that A is in B if and only if B is in A, modulo some U underscore things and so on. So that is Stone's original definition for Boolean algebras. So he starts with a Boolean algebra, so typically the free Boolean algebra of formulae. Yeah, the algebra of formulae with implication is not just a Boolean algebra, it's the free Boolean algebra on the set of atomic formulae, meaning that there's an adjunction, okay? Adjunctions arise everywhere, as Daniel Katz said. And so you take ultrafilters, define a topology on a topological space this way, and the space you obtain is a very, very, very particular kind of topological space called, nowadays, a Stone space, somewhat unsurprisingly. And a Stone space is a kind of topological space that ordinary mathematicians would frown upon. So it has so many strange properties. So it has very good properties. So for example, it's a compact Hausdorff space. But it's a zero-dimensional space, which is very bad for a traditional mathematician. That means its topology has a base of Klopen sets. A Klopen set is a set that is both open and closed. Good.
I'm loving it.
Oh, sorry, I should have said that to get a Hausdorff topology, you actually have... Oh, no, it's good. You have negations in the formula, so it's good. So, in fact, you can show that starting from classical logic, okay, this is a set of ultrafilters such that not F is in U, and by the general property of ultrafilters, which contain exactly one of formulae and its negation, and because all these things are quotiented by equideduction first, so not F is in U, if and only if not F is in U. So not F is in U, if and only if F is not in U. So that is actually the complement of the set of ultrafilters that contain F. And the funny thing is that this is open, this is open. So this is open, but it's also a complement of an open set, so it's Klopen. Okay? And sorry, I should have said that you define the topology on the space as with that as subbasic open sets. So the smallest topology that contains these open sets. The intersection of any of these sets. So the set of ultrafilters which contain both F and G, so they contain F and G, and conversely as well, because they are filters. So this is, sorry, indentation of F and G. So since they are closed under finite intersections, every open set is a union of finite intersections of things. Every finite intersection can be written as one of these things. For completeness, I should say that top is also the whole space. So all ultrafilters. So that means that also the nullary intersection is in it. So every open set is actually a union of sets of this form. So these sets form a base. A base means that every open set is a union of basic sets, not a union or not just a union of finite intersections. So you've got a base of your topology formed by these sets, and they are Klopen. That's called a zero-dimensional space. Also, I don't remember why there are two words, or perhaps I'm confusing two notions. It's also called a totally disconnected space. In French, totalement discontinu. So, yeah. That means in particular that geometrically, so that means that you can't have any geometric intuition about that kind of space. Because essentially that means that if you take any two distinct points, because, so essentially because it's Hausdorff, there's an open set around each point and they don't meet. And these open sets contain even further basic sets, so I can assume that these sets are basic. But in fact, instead of having two sets, this set is Klopen. So its complement, which is the open defined by not F, is larger than the one defined by G, contains this point, and this one contains this point. So what that means is that there's a Klopen set, which is this, which contains one point and not the other one. So maybe you remember from topology a long time ago, not here, that a space is connected if and only if you can't write it as the union of two disjoint open sets, non-empty. So the idea is that if you do, okay, the real idea about connectedness is that categorically you can form the co-product of any two topological spaces, but typically that co-product, whose topology is just, you take all unions of an open set from here and an open set from there. Geometrically, that means you put the two topological sets side by side and they're completely separated. Okay? And a connected space is a space which you can't write as a co-product of two non-empty spaces. Meaning that it's just one big blob. Okay? There's no way of cutting it in two along a place where which you could
separate.
Yeah. So an equivalent definition is a space is connected if and only if you can't actually write it as the union of two non-empty open sets which are disjoint. And in that case, you can separate any 2 points by two such open sets. So it's incredibly disconnected.
Yes.
You can disconnect any pair of points.
Yeah.
That's why it's called totally disconnected, of course. But don't confuse that with another notion called extremely disconnected, which is different.
Extremely interesting.
So anyway, the original stone duality takes a Boolean algebra, builds a space of ultrafilters with that topology, you get a stone space. And conversely, if you take any stone space, it has a base of compact open, of Klopen sets, and this base of Klopen sets with inclusion is a Boolean algebra. Okay? The complement of a Klopen set is Klopen. Okay? The intersection of two Klopen sets is Klopen, and so on. So it's a Boolean algebra. Okay, so you have a category of stone spaces in continuous maps, a category of Boolean algebras and Boolean algebra homomorphisms, that is, homomorphisms that preserves absolutely every connective. Okay? And there's an adjunction. Okay? I've described how you can go from Boolean algebras or even Boolean pre-algebras to stone spaces, and from stone spaces to Boolean pre-algebras. And this is an adjunction. And this is even better than an adjunction. It's a so-called adjoint equivalence, meaning that the unit eta of the adjunction is an isomorphism of topological spaces, and that the co-unit epsilon is an isomorphism of Boolean algebras. But what is the connection with what I've told you earlier? Well, the connection is a funny thing that Simon Alphon, who is not coming any longer, so it's I'm using that opportunity to do just like that's about in old China, to make some to put the shame on absent people publicly, you know.
But you're registered.
Yes.
So
So
do
I hope readers
it
don't
the right
understand,
way.
haven't understood the name I've just uttered, but Simon, who is a great guy. So
Anyway.
he finished a PhD thesis last year, and his PhD thesis is about something that was used typically in domain theory, but he used it in verification. It's called the ideal completion. Okay, so let me tell you about ideals and the ideal completion. I'm not sure we can see a lot with that then. I've actually already told you about ideals a long time ago. And certainly I have told you, so if X is a poset, let X be a poset, there's a notion that's fundamental to domain theory called a directed set. So a directed set is a set, first, which is non-empty. That's very important. And I'm saying that because I'm saying that to all my students every year when I teach them that. And I tell them that they must not forget to check that their set, which is meant to be directed, is non-empty. But since it doesn't look to be the important thing, they always forget about it. And I try to scare them by telling them that if you write in an exam that is directed because of the second condition I will illustrate, but you forget to tell me it's non-empty, I will remove at least half of the points. And still some people forget to verify it's non-empty. Anyway, so a directed set is a non-empty set which has a property that if you take any two elements in the set is the form, well, you can find another one which is above the first two, and which is still the directed set. So in Greek, a directed set D is a set that is non-empty, and such that for all elements to x, y in D, there exists an element in D. That is also something which you shouldn't forget. Some students each year say, oh yes, sure, just take top. Yeah, but top, is it in that set D? No. So such that x and y are both below z. So that's used in domain theory because essentially a directed set is an abstraction of a process by which, if you imagine that the ordering is the information ordering of Scott, that is, x is below y, if y gives you more information about some ideal computation than x. So typically the example I usually give is, I used to build some crossword puzzles at some time, and I was using a program that I had gotten from the net, which I have completely modified, and now I'm not building any crossword puzzles because I've made a stupid mistake of making one modification too many, and I had forgotten to save the previous ones. So the one modification too many made it fail to work, and I forgot what I had done, and really stupid. And anyway, so anyway, that program works this way. The user tells the program, I want a grid of that shape, a square grid, for example, a 15 by 15 grid, and the user tells the program, I want black squares here, 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 and there. So the program will never change the black squares. And it's a bit funny, by the way, that if you want to build a crossword puzzle, it's exactly the way you should do it. That is, you should actually fix the grid with the black squares. Well, at least for American-style crosswords, and also English, British crosswords. For French crossword puzzles, it's different, and it doesn't work this way. But typically for American crossword puzzles, you would fix the distribution of black squares. And oh, by the way, because it must obey a certain number of constraints, the New York Times puzzle, if you look at them, most of them, not all of them actually, some of them are brilliant and try to work with exceptions, but typically they're symmetric. They're symmetric across the diagonals. And there are other constraints, like there shouldn't be any consecutive sequence of just two white squares, and a few others. So you draw your grid, and then you launch the program. And the program essentially draws a position at random, says, oh, I would like to find a 7-letter word, looks into its dictionary, finds a word at random of length 7, and then we'll try to fill the rest of the grid this way with some heuristics. Okay? And if you launch that program, well, if you're lucky, which happens typically if your grid has a nice distribution of black squares, it will stop rather fast, and otherwise you will have to wait. And one thing that you could do in that program was to type something like control something. It sent a signal to the program, and instead of stopping the program would show you what the current state of the grid is. And typically, if you send that signal to the program too early, it will show you an empty grid. You have to be really fast for that. I'm not fast enough. And if you wait until the end, you'll get complete grid or failure. Okay? But if you type control whatever in the middle, you'll see a partially filled grid or a grid that's more filled, and so on. And you can define the information order on grids by saying x is below y if and only if x is less filled than y, essentially. And you see that computation, that's the intuition that Scott had, is that instead of describing the semantics of programming languages by telling you the final values, completed grids, you should also take into account all the partial values that you would get if you inspected the state of the program before it ended. And typically, what he came to in 1969, in a fantastic paper, by the way, called The Type Theoretic Alternative to iSwim, Kuch, and OY, and which is one of the most famous and most used paper ever, especially among those papers that have not even been submitted. So it was eventually published. It was published in 1990 something as a collection of the most the papers with the most impact in the last 20 years, something like that. But it had never been published before. In fact, it had never been even submitted. I'll tell you the story another day. And that was actually a pamphlet. Okay? Scott actually wanted to say that an approach taken by people in the lab where he was completely wrong. And he said that here's the right way to do it. And the problem is that the right way to do it was also a justification for the wrong approach. So he realized that his argument was actually negating itself, so he didn't even submit it. But anyway, he invented domain theory this way. Mm-hmm. And so he said, the fundamental thing is that your space of values should be a so-called DCPO, meaning directed complete partial order. A partial order is just a pose set. Okay? It's a set with a partial ordering. And it's directed complete, and the definition of directed complete means that if you take any directed set, which essentially gives you a process of elements that goes up, okay? So chains in particular are such processes, but it turns out that mathematics is kind of more elegant if you don't just take chains, but also directed sets, where in a directed set maybe you have two partial pieces of information, but they are consistent in the sense that there's a further piece of information which is above the two which is still in the set, and you can refine the information this way. And what you require is that for every directed set D, D has a supremum, so the supremum of D exists. And that's the basic structure in domain theory. This is just a parenthesis. Domain theory is actually pervasive in topology. The funny thing is that you discover things today in topology which have domain theoretic components, but also, and that was one of the domains of expertise of Klaus Keimel. Klaus Keimel was a German mathematician, and he died something like 1 year ago, or yeah, something like that. And he was an expert into rephrasing famous theorems of mathematics and discovering the domain theoretic contents. And one of the last things he did was to explore the so-called sorry, I don't remember how it's called, but it's a theory that's meant to show the existence of trace operators in Banach algebra, in Banach spaces, and further. And the basic construction is a semigroup. Oh yes, the Kunz semigroup. And the Kunz semigroup is actually built from a domain theoretic construction, which is called the rounded ideal completion. That was not built this way, but he discovered that the way you build it is by a rounded ideal completion. And rounded ideal completion is a variant of the ideal completion I'm going to describe now. So here's a funny construction you can do. Let X be a pose set again. Now let me define a new pose set, which I will call I of X. And I of X consists of all the ideals of X. What is an ideal? Oh, an ideal I is a directed set which is downward closed. So it's a set like this, but each time you have a point, you also have all the points below. And by the way, it's an easy exercise to show that a DCPO is also exactly the same thing as a pose set in which every ideal has a supremum. So if every directed set has a supremum, every ideal being directed has a supremum. And if every ideal has a supremum, now take every directed set, take its downwards closure, so all the points below some point in D, that is an ideal. And it must have a supremum, and that supremum must be the supremum of the original set. So let me take the set of all ideals ordered by inclusion. I claim that this is a DCPO. Oh, now it's becoming to be hard again. Okay. It's a DCPO, but a DCPO you have to find directed families. Okay, and these are directed families of ideals, which are themselves directed. Okay, so there are two levels of directedness. But okay, ignore the complication. Just do the math. Let I sub j, j being in some index set j, be a directed family of ideals. So that means there is an ideal in it, and that also means that, so it's non-empty, plus, if you take any two indices j and k, so any two elements ij and ik in there, well, there's an element, I don't know, I didn't want to take small I, but now, there is an M, okay, such that ij and ik are both below, that is included in in. Well, I claim that the union of all the ij's, fortunately the supremum is not that hard. It's just a union. Okay. I write this to say it's a directed union to remind you of that. So this is an ideal, and this is the supremum of the family in the collection of ideals. Okay. In fact, as soon as I've shown that it's an ideal, it will be the supremum. Ah, why so? Okay, imagine it's an ideal. It certainly contains every ij, so it's an upper bound. Imagine, to show it's a least upper bound, let me take any upper bound of that family, I. So I contains every ij. Hence, I will contain the union of the ij's. And that will prove that it's the least upper bound. So the only thing I really have to show is that this is an ideal. Okay, it's non-empty because J is non-empty because it's a directed family. So there's an ij, and that ij is non-empty. Okay, so that union is non-empty. Okay. Is that directed? Okay, directed. So let me take any 2 points x and y in the union of the ij's. So x is in the union of the ij's. So x must be in some ij. Y must be in some ik. Oh yeah, probably not the same one. But I don't care because that family is directed. So there's an M such that IM contains both. And now x and y are in IM, and IM is directed. So there is a Z above x and y in IM.
Yeah.
And hence it's in the union of the ij's. Okay. Final thing, you have to show that it's downwards closed. So if you take any point in it and a point below that, it's still in it. Okay, easy, right? Well, if it's in that union, it's in some ij, and so the point below is also in ij, hence in the union.
Okay.
So that is a DCPO.
Right.
That is an incredibly nice DCPO. Yes. It's a DCPO that is what we call algebraic. And that's the kind of thing that people starting domain theory look at with awe, or with or they're scared by it. Yeah, with fear, exactly. That's the word I was looking for. And okay, so instead of giving you the definition, so I'm lacking a bit of space, but later I will write something. So for now, I will use that space. Okay.
Which is sober enough.
Look at, for every x in big X, look at the set of points below x. I claim this is an ideal. It's non-empty, it contains x. If you get 2 points below x, there's one above both of them which is below x, just x.
X.
Okay? Mm-hmm. And it is downwards closed. So this is an ideal. Well, in fact, you have a map which goes from x to the ideals on x, which I would like to call eta, but because it's the unit of an adjunction.
Well done.
So I won't actually prove it, but if you want to know a bit more about adjunctions, I urge you to show that I of x is the free DCPO over the poset x. And that is the unit of the adjunction.
Great.
In fact, that's not completely surprising, I mean, because essentially what you've done is, so let me do a kind of parallel with Cauchy completion of metric spaces. Unless you don't remember.
I don't.
You don't. Okay, so let me not make a parallel with
No, yes,
Cauchy
please
completion.
do.
So okay, so Cauchy completion is the following thing. You want to build the free complete metric space over a metric space. It's again an adjunction. So, okay. So, okay, let's say it another way. That you start from a metric space, you want to add points so that it becomes complete. So the problem with your metric space is that there are some missing limits. Okay? And the missing limits are limits from so-called Cauchy sequences.
Okay.
And so what you do typically is you take the space of all Cauchy sequences and you declare that a Cauchy sequence is the representation of its own limit. Okay, that's the typical thing you do in mathematics. You have to tweak things a bit. So typically you have to do very complicated things. Well, they're not complicated, but they require some effort. So typically you have to define a metric on the set of Cauchy sequences. And it's not going to be a metric, that's the problem. So you have to tweak that a bit more. So typically what you do is you take two Cauchy sequences and you say the metric is going to be, so xn and yn, and you say the distance between the two is going to be the, not supremum, what is it already? So something where you compute the distance from x0 to y0, the distance from x1 to y1, and so on, gives you a sequence of numbers, and you take something like the lim sup of that. Okay? And it's not a metric because there are plenty of Cauchy sequences which are at distance 0. So you may converge to 0 from above, from below, and this is two Cauchy sequences, and their distance is not going to be 0. So their distance is going to be 0, but they're different. So you take the quotient of all Cauchy sequences with respect to being at distance 0. That makes it a metric. And then you have to show that this gives you a complete metric space, which is a bit complicated because you have to take Cauchy sequences of equivalence classes of Cauchy sequences. Okay. So, but this is essentially what we've done here. Okay, we've taken directed families of ideals which are directed. Okay, so there's some kind of familiarity. Okay. So here it's the same thing, but it's simpler.
Yes.
What we want for a DCPO is that every directed set has a supremum. Or as I said, every ideal should have a supremum. So we do the same trick. We say, oh, we just say that an ideal is the supremum of itself. Okay? Modulus of isomorphism. Yeah, okay, so we freely add all suprema of ideals by just taking all ideals. Okay. Why do we take ideals instead of directed sets? Well, because it simplifies the quotienting part.
Yes.
The point is that what you want really is that two directed sets. You would like, if you did that just like for Cauchy completion, you would say, I would take the pre-ordered set of all directed families, and I would like to compare them, and eventually you realize that two directed families should be equivalent if and only if they are mutually cofinal. That is, for every element in one, there's a higher element in the other one, and conversely. And then you realize that it means that the downward closure of both are equal. So you have a canonical representative of your directed family. It's the ideal obtained by taking the downward closure. So instead of doing quotients, just take ideals directly. Yeah. Okay. And excuse me?
I'm wondering if instead of taking the downward closure, we could either take a kind of minimal set, giving you the same downward closure. Kind of generating.
No, that doesn't exist. No.
How that doesn't exist?
Well,
I mean, it is.
Imagine you take.
Used, but
No, it does. There's no minimal set generating this.
No minimal set.
No, it's not well founded. So
I mean, you take a downward closed set.
let me give you an example.
Yes, please.
Imagine I'm starting from the following Poe set. It's a set of rational numbers with usual ordering.
Yes.
Okay. All the numbers below square root of 2, or any rational number, forms an ideal. Okay. Can you find a minimal set of rational numbers such that its downward closure is all the numbers, the rational numbers below square root of 2?
At least the set itself, but it's not minimal.
It's certainly not minimal. It's the maximal one.
Yes, but among those sets, isn't it
No.
one which is not?
No, because every set that has this property must contain infinitely many elements with an accumulation point at square root of 2. And if you remove any point of that, you get an even smaller set, which has the same property. So there's absolutely no minimal set generating that ideal.
Typically, you have no minimal infinite set of natural numbers.
Exactly, that's the same thing. No minimal infinite set of natural numbers. But you have a maximal one. So why should we?
Worry.
Yeah, why worry? No, really, we don't have any minimal thing. I can understand your concern. This is a typical computer scientist concern. We want minimal objects. We want representable objects. They have to be small. In mathematics, you do exactly the opposite, okay? You take maximal objects when they're canonical because they're canonical. You don't care whether they're large, they exist, that's the point. No, after that, I was mentioning Simon Alphon. What he did in his PhD thesis was to show that for certain classes of spaces X, which are well quasi-ordered sets, you can actually represent the set of all ideals through a certain kind of syntax. So, and that is more satisfactory. You have a kind of canonical representation. It's a finite piece of text.
Well, a down arrow is also a finite piece of text.
Yeah, but the point is, of course, when you, I've plenty of implicit things in what I said, but typically when you speak about computer representations, you think about computer representations that are representable and on which a certain set of functions are computable.
Okay.
Which I haven't mentioned. So anyway, we have this map, which is actually the unit of the free DCPO monad, but eta was already taken, so let me use Xi today. This is a map from X to I of X. So I've just said, something like 10 minutes ago, that down arrow X is an ideal. So it's indeed a map from X into I of X. And it has plenty of properties. For example, it's Scott continuous, but I haven't said what Scott continuity is. So that will be for another day. What I wanted to say is that I of X is an algebraic DCPO. And here's the explanation. Look, this object has a fantastic property. It's a property where I won't use any element. It's just like in category theory. You say for every ideal, for every whatever. So, look, if I take any directed family of ideals, and imagine that down arrow X is below, that is included in the union of the ij's. What can you say? You already know the answer, Louis. So I'm going to do like the ordinary school teacher. Only the people who don't know have the right to say something. I want to make you yourself feel miserable, you know. So Loic, I know you know the answer.
Yes, sorry.
Okay, so what can the others say? So Valentin, you know the answer as well.
Sorry, I didn't get the question.
So the question is, imagine I have a direct family of ideals whose supremum, which is the union, contains down arrow X. What can you say?
If you know the answer, you're not allowed to say it.
Absolutely, absolutely. But please, the others who don't know anything, please say anything dumb. No, I mean, let's go to the end of the same logical argument. Okay, so certainly X is in there, right? So X is in there. So X is in some ij. But ij is downwards closed. So down arrow, there exists a j, such that down arrow X is included in ij. Okay. Okay. So essentially what we have is we have an ideal. Don't care whether it's an ideal or not. It's an element of the DCPO. You start from an element of the DCPO, which is down arrow X, and you have that property that if you take any process whose limit goes above that, there's no other way that at some finite point in the process you must have already gone above that. Okay? So the definition, let me erase this. In a DCPO, let me call it Y, an element Y is finite. Some people say compact, and there's a good reason for that. It's related to topology. Okay. If and only if that funny definition, which is essentially this one, for every family Yj of elements which is directed, if Y is below the supremum of the Yj's, direct supremum, then there is a J such that Y is below Yj. So a finite element is an element that's so small that the only way to get above it in the limit is to get into it after some finite time. Okay, claim the finite elements of the ideal completion are exactly the ideal, so these things are called the principal ideals. Down arrow X. There's no other one. So let me see if I can find the proof. Well, that's in fact extremely easy. That's almost a tautology, actually. Let me use, okay. Here's an ideal. I don't know whether there's a point on top of it, okay? That's what I want to prove. But let me assume it's finite. Before I'm using the finiteness assumption, notice that every ideal can be written as the union of the downward closures of X for X in the ideal, right? That means that every point in the ideal is below a point in the ideal. And conversely. Now notice that this union is directed. It's directed because each time I have an X in the ideal and a Y in the ideal, downward closure of X is there, downward closure of Y is here. And there's a point Z above X and Y, and certainly the downward closure of Z contains these two downward closures. And it's not empty. Huh?
And it's not.
Okay, now let's use finiteness. I is a finite ideal. It is included in a directed union of ideals, so it must be included in one of them. Okay, so I must be included in down arrow X for some X in I, and down arrow X is included in I, so they're all equal. So I equals down arrow X. Okay, so the finite elements of the ideal completion gives you back the original space, the original poset. And now you have, well, let me reuse that property. You have that every element of the DCPO I of X, every ideal, is a directed supremum of finite elements. These are finite. Okay, that is the definition of an algebraic DCPO. An algebraic DCPO is one in which every element is a directed supremum of finite elements. Why am I saying that? Well, just because I wanted to talk about ideals. And conversely, you can show that every DCPO which is algebraic is isomorphic to the ideal completion of its finite elements. So in fact, an algebraic DCPO is up to isomorphism the ideal completion of something. That's exactly the same thing. But now let's return to logic. Why have I mentioned the ideal completion? We were talking about ultra filters in blue, and suddenly I talked about ideals. Oh. I think I can erase this now. Take a prime filter. Okay, this will handle the general situation. A prime filter, okay, in, well, I have never named my whole set of formulae, okay, but in general it works for any pre-Boolean algebra or even a pre-distributive lattice, meaning something whose quotient by the congruence associated with the ordering is a distributive lattice. So let me call it omega, space of formulae or something like that. Consider the complement of u, omega minus u. Okay. Is that, oh sorry, I should have said that a prime filter, this is typical, but you know, earlier I said for directed families you should check it's non-empty, and there's a similar mistake I have done in that case. A prime filter is a filter which not only has this property that if f or g is in it, then f or g is in it, but also that the filter is proper, so that its force is not in it. Okay, and that was probably implied by other things, but I don't know. Well, okay, that was written here. Okay, so false is not in it. False is not in you, so false is in there. So that thing is non-empty. Okay? A filter is upwards closed, so its complement is downwards closed.
Okay.
Okay, so now you think, you say, oh, he's going to show that it's directed. Oh yes? Imagine that directed. So to show it's directed, you take f and g in the complement of u, and you want to show that there's a formula above f and g, which is also in the complement. Well, I claim that f or g is in the complement. Why so? Well, take the contrapositive of this. It says that if f or g is in u, then f is in u or g is in u. And this is what we have written here. Okay? So the complement of this prime filter is an ideal. Okay? It's even better than that. Remember meet prime elements? When we did stone duality, I told you, well, one of the ways you can define a set of points is by taking completely prime filters, or you can take meet prime elements of your lattice. So what I claim is that omega minus u is a meet prime, I'll write what meet is later, of the space of ideals of omega. So meet is in infimum, it's intersection. Okay, let me check that. So that means that the definition is, well, first, this is not top. This is not the top element. Okay? And there is a top element in I omega when omega is a distributive lattice. It's just it's just the principal ideal down arrow top, which contains everything. Okay? So I claim first that this is different from the whole thing, down arrow top. The only thing you have to check is that top is not in it. And it's not in the complement because it is in the ultra filter, which is what we wrote, hopefully. No, I just said that it was non-empty, and since it was closed, it contains top. Okay, so it's not the top element, and then the other property is that if you take any two elements, which are ideals here, I1, I2, such that they meet I1 inter I2. Oh, sorry, I should have said that the meet of two ideals is an intersection because the intersection of two ideals is again an ideal in a sub-semilattice. So if you have an OR, this is true. And so you want to show that if that is below, that is included in omega minus u, then I1 or I2 is included in omega minus u. Okay, I hope it's true. So, what does it mean to be included in omega minus u? That means it doesn't meet u. Okay, so that is equivalent to saying for every I1, I2, okay, let me say that slowly. Blah is included in complement of u, means that for everything in blah, it's not in u. So blah doesn't intersect u. So what we want to show is that if y1 inter I2 doesn't intersect u, then I1 doesn't intersect u, or I2 doesn't intersect u. I'm missing a bit of space here. But of course, take the contrapositive. And now that means for every I1, I2, imagine, and I'm going to do a bit of a drawing. So you have two ideals, I1, I2. Okay. So if I1, sorry, it's empty, and now we take the contrapositive. So with the contrapositive, you get non-empty things. So if I1 inter U is non-empty, okay, so U is somewhere here, and it intersects I1 here. And if I2 intersects U, let's say here, then I want to show that I1 inter I2 intersects U, which of course is not the case in the picture. Yes. Well, you have 2 points here, x and y. So there's, oh, sorry, I called them formulae earlier, f and g. So if you have a new one, f and g, conjunction, it's in u because u is a filter. But FSG is below f, so it's in I1, and it's below g, so it's in I2. So f and g is somewhere here. It's in the intersection of I1, I2, and u. So that property is true. Omega minus a prime filter is a mid prime element of the ideal completion of omega. Now, if you look closely, taking all sorts of complements everywhere, those sets we have defined are exactly up to that isomorphism, the basic open set we had taken to define PT, but instead of starting from omega, we start from the ideal completion of omega. So the point, and I think we can stop here for today, is that the stone dual we had here, this is up to isomorphism. This is PT of the ideal completion of omega. And now I'm going to stop here by telling you, okay, we've reached a kind of mystery where we see that we do various constructions in logics. They produce some kind of ultrafilters. These ultrafilters are the element of the stone dual, and the stone dual is what we had written earlier as PT I omega. So it's not PT of our original set of formulae, it's PT of its ideal completion. And next time, if you agree, We haven't used Zorn's lemma at all here, right? But Zorn's lemma is needed. To prove completeness, you need to use that axiom of choice. So something will require Zorn's lemma or the axiom of choice somewhere. And that something is going to be that if you start from an algebraic frame here, oh, sorry, I should say, when omega is a distributive lattice or a pre-distributive lattice, I omega is not only an algebraic DCPO, it's even a frame. And next time we will show that it is a spatial frame, so that it is actually isomorphic to the space of open subsets of its space of points. So the co-unit of the adjunction is actually an isomorphism of frames. Okay? And that requires Zorn's lemma. And then we'll show that the unit is also an isomorphism, meaning that the space we've gotten is sober. And I'll show you why completeness is a consequence. I'll also tell you why this implies what people usually say is Stone's theorem, that is every Boolean algebra, there are several ones, but every, let's say, Boolean algebra is a sub-Boolean algebra of some power set. That is actually a trivial consequence of all that as well. And I'll stop for today.